Hello everyone, this is Behura presenting before you my final project for wireless communications. My final project is a comparative analysis of MIMO systems using MRC and Alamouti STBC schemes. Let's go through the contents of the presentation: introduction, overview of MIMO systems, maximal ratio combining, Alamouti space-time block coding, singular value decomposition, water filling algorithm, simulations, analysis, and conclusion. In recent years, wireless communication has played an important role in changing the lifestyles of people. Wireless communication systems can be seen everywhere, including mobile phones and satellite operations. But wireless communication systems face a number of problems, like interference and multipath fading. Fading is the term given to the attenuation on the signal when it travels through a transmission medium. Multipath propagation is a result of reflection and refraction caused by obstructions on the signal path. There are many solutions to multipath fading. One of them is the diversity scheme. The diversity scheme uses a number of channels for transmission of signal from the transmitter to the receiver. This is what we are going to consider in the project. This is a good point of time to introduce to you the term diversity gain. Diversity gain is the signal to interference ratio, which can be measured in decibels. There are different diversity schemes such as space or antenna diversity, time diversity, and frequency diversity. In this project, we get into details of space diversity schemes. The space diversity scheme uses more than one antenna at the transmitter or receiver to send multiple copies of the signal and eventually improve the diversity gain. Before we get into more details of the space diversity technique, we need to know the different antenna systems available to us. They are CISO, MISO, CMO, and MIMO. The MIMO systems have multiple input and multiple output antennas. Why do we use MIMO systems over the other systems? The MIMO system offers significant increase in data throughput and link range without any need for extra bandwidth. The MIMO systems are used in IEEE 802.16e standard. They are also being used in mobile radio telephone standards like 3GPP, 3GPP2, and LTE and non-wireless communication systems like home networking standard ITU-T-G9963. The MIMO system can be represented using the matrices as shown below. A MIMO system has R receiver antennas and 3 transmitting antennas. The output signal received at the receiving antennas can be represented by the Y matrix, which has R terms, Y1, Y2, and so on till YR. X1, X2, and so on till XT are the signals transmitted from the various transmitting antennas. N1, N2, and so on till NR are the noise signals at the receiving antennas. The H matrix has R rows and T columns and is also known as the channel matrix. The final output received at the receiver is given by the channel matrix into the input plus the noise signal. The different categories of the MIMO system, they are precoding. Precoding is a beamforming technique that is used to increase the gain of the received signal by adding the signals from different antennas constructively and thus reducing the multipath fading effect. Spatial multiplexing, it is a powerful technique where a high rate signal is divided into multiple lower rate signals. Diversity coding, a technique where a single stream being transmitted is coded using different techniques to enhance signal diversity. An important concept to go through here is the singular value decomposition. Singular value decomposition is used so that the channel matrix is broken down into singular values for simpler calculations. Here we consider an equal number of transmitting and receiving antennas, which is equal to T. The singular value decomposition of the channel matrix is given by H equal to U sigma V Hermitian. U and V are unitary matrices and H is the channel matrix. The sigma matrix depicts the various singular values obtained. The conditions for singular value decompositions are U and V should both be unitary, and sigma 1 should be greater than or equal to sigma 2, should be greater than or equal to sigma 3, and so on till sigma t. And all these sigma values should be greater than or equal to 0. Here, the signals do not interfere with each other at the transmitter or the receiver, and hence this is also known as logical beamformation. Next, we look into the water filling algorithm. It is very necessary to optimally allocate the power to different channels. The total capacity of the channel is given by the Shannon's theorem, which is equal to sigma I equal to t, 1 to t log base 2 1 plus pi sigma I square divided by sigma n square. Sigma n is the total noise power. Sigma I is the singular value of the ith channel of the channel matrix. Pi is the power of the ith channel of the matrix. The optimal power allocated to each channel is obtained using the Lagrange's method. As we can see from the figure on your right, when the power in a channel exceeds the threshold, which is 1 by lambda, then the power allocated to the channel would be 0. And if the power of the channel is below the threshold voltage, then the power will be optimally allocated. Moving on to different diversity schemes we have considered here. The first one is the maximal ratio combining. Maximal ratio combining is one of the combining techniques that mitigates the effect of multipath feeding. The most efficient way to use information from different paths to achieve decoding in additive wide Gaussian channel is MRC. The receiver corrects the phase rotation caused by feeding channel and then constructively adds the received signals of different paths in proportion to the signal strength. As signal traverses through different paths, each of them undergoes a different amount of attenuation, and combining these with different weights yields an optimum solution. Although MRC is better in mitigating the effect of multipath fading, it is more complex than the earlier used techniques. So we move on to the next technique, which is the Alamouti STBC technique. Alamouti STBC is a transmit diversity technique unlike the MRC, which is a receive diversity technique. This technique aims to reduce the bit error rates by transmitting multiple copies of the same data through different transmitters. Since the same data is sent through different channels, the data suffers from different amounts of distortion as the channel loss and scattering through different channels vary. Multiple data is transferred through different channels to achieve a higher data rate. A Alamouti STBC 2x1 system has 2 transmitting antennas and 1 receiving antenna. In the first time slot, the 2 transmitting antennas transmit x1 and x2. In the second time slot, the 2 transmitting antennas transmit minus x2 conjugate and x1 conjugate, respectively. The Alamouti 2x1 system can be represented as follows. The output received at the receiver antenna in the first time slot can be given by h1x1 plus h2x2 plus n1, where h is the channel matrix. x1 and x2 are the transmitted signals in time slot 1 by transmitting antennas 1 and 2, and n1 is the noise at the receiver. y2 is the signal received by the receiver in the second time slot and is given by minus h1 x2 conjugate plus h2 x1 conjugate plus n2, where h is the channel matrix, minus x2 conjugate and x1 conjugate are the signals transmitted by the transmitting antennas 1 and 2 in time slot 2, and n2 is the noise power in time slot 2 at the receiver. W1 and W2 are required for decoding the signals transmitted in time slots 1 and 2. These values are as given in the equations. W1 Hermitian y equal to h double bar x1 plus n. This is here y is the total transmitted symbol in the total time interval. Thus, from this equation, we can see that the received symbol is dependent only on the signal transmitted by signal 1. Thus, the signals do not interfere with each other at the transmitter or the receiver. The second scheme we consider here is the Alamouti 2x2 scheme. Here, there are 2 transmitting antennas and 2 receiving antennas. Thus, there are a total of 4 signals received at the 2 receivers in 2 different time slots. In the first time slot, the receiver 1 and 2 receive the following signals: y1 equal to h11 plus x1, y1 equal to h11 into x1 plus h12 into x2 plus n1, y2 equal to h21 into x1 plus h22 into x2 plus n2. y1 and y2 are the received signals at the receiver 1 and receiver 2 in time slot 1. Similarly, in time slot 2, the signals received are y1 square, which is equal to h11 into minus x2 conjugate plus h12 into x1 conjugate plus n1. y22 is given by h21 into minus x2 conjugate plus h22 into x1 conjugate plus n22. Here, y12 and y22 are the signals received at the receiver 1 and 2 in time slot 2. Hence, the total number of received signals, which is equal to 4, is given by the Y matrix on the right, where H is the channel matrix, X1 and X2 are the transmitted signals by transmitter 1 and 2, and N is the noise matrix, which represent the noise power at receiver 1 and 2 respectively in time slots 1 and 2. The first simulation that we did was for maximal ratio combining. It was compared to the one transmitter, one receiver antenna. We could see that the maximum ratio combining technique with one transmitting antenna and 2 receiving antennas performed a lot better. Second, we measured MRC signal, the signal to noise ratio with the MRC technique, and we increased the number of antennas. As we increased the number of antennas, the signal to noise ratio gain increased. Thus, we realized that as we increase the number of antennas, the signal to noise ratio increases. But this can only happen till a particular number due to practical constraints. The next simulation, we compare MRC scheme with Alamouti, one transmit 2 receiver antennas, and a CISO. We can see that the MRC scheme performs better than the Alamouti scheme, and the Alamouti scheme performs better than the CISO technique with one transmitting and one receiving antennas. The MRC scheme is actually performing 3 dB better than the Alamouti scheme. The next simulation we go through considers the MRC scheme, the Alamouti 2x1 scheme, the Alamouti 2x2 scheme, and the CISO scheme. We can see that the Alamouti with 2 transmitting antennas and 2 receiving antennas performs the best. The second best is the MRC scheme. The third best is the Alamouti 2 transmit 1 receive antenna scheme, and finally the single input antenna and the single output antenna. The observations that could be made through the simulations were: the MRC performs 3 dB better than the 2 transmit 1 receive and Alamouti space-time block coding. The 2 transmit 2 receive Alamouti space-time coding is better than the 2 transmit 1 receive Alamouti STBC. For a system with NR antennas, the diversity order of 2 transmit Alamouti scheme is 2NR. In Alamouti scheme, there is no crosstalk between the 2 transmitted signals due to the presence of diagonal matrix. For the MRC scheme, as the number of receiver antennas increases, the signal to noise ratio increases. The 2 transmitter 2 receiver Alamouti STBC scheme performs better than both the maximal ratio combining and 2 transmitter 1 receiver scheme, and it obtains a diversity order of 4. There are different. Let's take a look at the advantages and disadvantages of Alamouti code. The advantages are, since multiple copies of data are being sent, there is a good probability that the signal will be received and there will be no data loss. Secondly, it achieves a diversity gain of 1 without any decrease in data rate. The disadvantages, though, are that the hardware size could be large and may cost more than the other schemes. Moreover, the latency reload related to the decoding stage is proportional to the symbol time diversity. The conclusion from the project is that MIMO systems can be divided into 3 categories known as pre-coding, spatial multiplexing, and diversity coding. The Alamouti STBC scheme in a 2x2 system has better BR performance as compared to the Alamouti STBC scheme with 1 transmitter and 2 receiver system, as well as better than 2 transmitter 1 receiver MRC system. Thank you.